Hello guys, am I audible? Am I audible? Yes. Okay. So we'll start today's session, and today's session is for structures. So let's start today's session, guys. Okay. Yes, guys. So today we are going to discuss. Today we are going to discuss GATE 2016 structures module detailed solution. Okay. So about me, myself, Dinesh Kumar, and these are my credentials. Okay, so the voice is clear. Am I audible? Okay. So I got AR 41 in GATE 2009 and pursued my master's at IIT Madras, and I have been guiding GATE Aerospace aspirants from more than last 10 years. So today's session, as I told, it is for GATE 2016 aircraft structures module detailed solution. So in this structures module, we will be covering three subjects, as I told: SOM, mechanical vibration, and we'll be also covering thin walled structures part. Okay. So you guys are free to interrupt me for any doubt or concern. So if you take the weightage, basically actually it is total 11 questions they asked, 5 for 1 marks and 6 questions they asked for 2 marks. So if you see the first question, it is from basic SOM, strength of material, or basic elasticity. So what it says, the total number of material constants that are necessary and sufficient to describe the three-dimensional Hooke's law for an isotropic material is. So guys, basically the Hooke's law or constitutive laws are what? The relationship between stresses and strain, right? Stresses and strain. So relationship between stresses and strain for isotropic material is given by how if you write those relationship. So you can write strain in terms of stresses, epsilon x, epsilon y, and epsilon z. So these are nothing but like sigma x by E minus nu times like sigma y plus sigma z by E, and then epsilon y is sigma y by E minus nu times sigma x plus sigma z by E, and then the third relation is sigma z by E minus nu times sigma x plus sigma y by E. So these are three relationships between normal stress, and normal strains. Okay, for isotropic material. Okay. Then we have another three relations between shear stresses and shear strains. Shear stresses and strains. Okay. So those three another relationship, how we write, we know tau xy is what? It is z times gamma xy. What is your this tau xz? G times gamma xz. And what is your tau yz? It is g times gamma yz. Now guys, you can see what are constants you know here. If you see this stress strain relationship for three-dimensional Hooke's law, you can see the constants. What are constants we have here? Can anyone tell? We have constant, which is Young's modulus of elasticity E. We have Poisson's ratio nu, and we have modulus of rigidity G. So there are total three constants. But we know G can be written as what? E upon 2 into 1 plus nu, right? The modulus of rigidity can be written in terms of Young's modulus and Poisson's ratio. So is it clear, guys? So how many total independent constants are required? Can anyone tell? See, the total numbers are 3, but the number of independent, how many number of independent material constants, guys? Total, right? Total number of independent material constants are only 2 for isotropic material. So this is one of the repetitive question, guys. It was earlier also asked in gate aerospace, and it is also asked in gate mechanical as well multiple times. Now guys, if you take anisotropic material, can anyone tell how many material constants for anisotropic materials? How many material constants? Exactly 21. Now if you take, guys, for orthotropic material, how many materials constant, guys? For orthotropic material, 9. Very good. Now guys, for monoclinic material, in composite monoclinic material, how many materials constant? It will be 13, right? So these are the things you guys can remember and can answer quickly if it is asked in gate exam. So let's move to next question, what it says. So next question is again from basic elasticity. And as I told in previous class also, you guys must know what is plane stress and plane strain problems. Okay, thoroughly. Okay, so read the question. Determine the correctness or otherwise of the following statements A and R. What the statement A says, guys? In a plane stress problem, the shear strengths along the thickness direction of a body are 0, but the normal strengths along the thickness is not 0. So for plane stress problem, shear strain along the thickness direction of the body are 0, but normal strain along the thickness direction is not 0. So guys, what is plane stress problem? What is plane stress problem? Plane stress problem says stresses along thickness directions are what? Along the thickness direction are 0. Okay, so but thicknesses are 0. So if you see what are stresses which are zero? You can say sigma zz if z is my thickness direction, tau xz and tau yz are zero. So that means what? From this tau xz and tau yz, what we find, guys? What we find? Your shear strains also zero, right? Yes or no? But when sigma zz zero, okay? When sigma zz zero, but we know from stress strain relationship, what is your epsilon z? Z or epsilon z? It is sigma zz by E minus nu times sigma xx plus sigma yy by E. So what we see, guys, here, though sigma z is zero, but your normal strain is what? It is not zero. So the statement A is true or false? A is true or false, guys? It's true, right? It's true. Now read the stress statement R. What it says? In a plane stress problem, Poisson effect induces the normal strain along the thickness direction of the body. Thickness direction of the body. So what is plane stress problem? So this is what I discussed. This is due to Poisson effect. See, though my plane stress problem means you have only sigma xx, sigma xx here, and then sigma yy, sigma yy, okay, and you can have tau xy shear stresses. There is no sigma z, but still due to this Poisson effect, we can see epsilon zz is non-zero. So the statement R is true. Statement R is also true or false? Statement R is true or false, guys? Reply quickly. It's also true, right? Yes or no? So you can read both A and R are true, and R is the correct reason for A. So I think answer A is only correct. If you read other, A and R are true, but R is not the correct reason for A. No. Both A and R are false, wrong, and A is true, R is false, wrong. So what is the answer? If I do a poll quick, okay. So let's move to next question, guys. What it says? The question number 13 from GATE 2016. So this question is from thin walled structure. Okay, and you guys should know these basics as well. So what it says? Consider four thin-walled beam of different open cross-section as shown in the case 1 to 4. A shear force of magnitude F acts vertically downward at the location P. In all the beams, in which of the following case does the shear force induces bending as well as twisting? Induce bending as well as twisting. So guys, we know what is the shear center, guys? There is a concept of shear center in thin-walled structure for flexural bending. So shear center says if your shear force passes through shear center, there will be only bending, right? There is no twist. Now guys, we know if there is a cross section, and for that cross section, if there is any common junction, so that common junction is what? Shear center, right? Correct, guys? Yes or no? So that common such junction is what? Shear center for that cross section. So now if you say me, give me one example. So this L section. So in L section, you can see this is the common junction. So this will be shear center. Why this will be shear center? Because when you find the shear center position, see the shear flow of this section, suppose this 1 to 2 and this is 2 to 3. So 1 to 2 as well as 2 to 3 is passing through this point. So when you take moment equivalence, you will get zero moment about this point. So this point 2 is shear center. Now if you take T section, either it's a symmetric, or you can say this kind of T section or any T section. This is common junction, so this will be your shear center. Now if you take cross, so you can say this is my cross, so this is my junction point, so this is my shear center. But now if you take channel section, is there any common junction in this? No. So we know for channel section, usually shear center lies here. Okay. Now look the options given. See, the first case is L. So for L, we know P is your shear center, and now this F vertical load is passing through this P point. So it's a shear center, so it will not create any twist in this case. Now look case 2. Case 2 is channel section, and we know for channel section, shear center is somewhere here. So this P is not shear center. So when load passes through P, it will create both bending and twist. Okay. Now look case 3. For case 3, P is shear center. We know it's a T section, and if F passes through P, so it will create only bending. And case 4 is cross, right? So for cross also, P is the junction and P is the shear center. So when load, am I audible? Yeah. So the load passes through P, so that means it will not create any twist. So which is the case which create both bending and twist? I think case 2. So what is the answer, guys? What is the answer? B is the answer. B is the answer, guys. So let's do a poll. So B is the answer. B is the answer. Let's move to next question. So guys, make sure you guys understand the basics of shear center at least. Okay, if you are not comfortable in thin wall structure, like doing long calculation, but the basics like shear center you guys must know, because I think multiple times they have asked question on this concept. Simple question. So let's see next question what it says. The effective stiffness of the spring mass system as shown in the figure below is. So if you see this is a simple mechanics question, guys. Simple mechanics question. So in this question, you see this spring and this spring are in which combination, guys? Are in which combination? Those who are watching in YouTube can comment. This spring and this spring are in which combination? They are in series. They are in series. So for series combination, we know the equivalent stiffness constant K equivalent is always what? K1 K2 upon K1 plus K2. So what will be the K equivalent, guys? See, K1 is 2, K2 is 2, so it is 4 by 4, right? So how much it is? How much it is, Vasant? It is 1 Newton per mm. Now you can see this K equivalent and this is in which combination? In which combination, guys? Anyone can comment on you? Those who are watching on ITC channel, they are in parallel. So whenever any spring which is in parallel combination, then what will be the K final? So it will be what? It will be this K plus K equivalent. So what is this K? It is 4, and what is the K equivalent? We got 1. So what is the K final? It is 5 Newton per mm. So what is the answer, guys? What is the answer? It is 5 Newton, 5 Newton per mm. Clear? Any doubt in this? Again, guys, I am saying there are multiple questions based on this spring, spring systems in GATE Aerospace. Previously, also we have discussed questions like where when there were two masses, they were connected with a rigid link, and then there are springs connected. Okay, this is one of the question, and then there are some other question, guys. So we can answer these questions if we know basics. Next question, what it says? This question is from basic elasticity SOM, and the previous question is from basic mechanics. So what this question says, guys, a structural member support loads which produces a at a particular point a state of pure shear stress of 50 Newton per mm square. At what angle are the principal planes oriented with respect to plane of pure shear? So it's a theoretical question. If you know the basics, you can always say what is the pure shear case. If you draw on stress element, my pure shear is what? These are my stresses, okay? And tau is what? Suppose my shear stress. So this is the case of pure shear. You can see here in this case there is no normal stress, right? So we know always for case of pure shear, my principal plane will be oriented at what? Pi by 4 and minus pi by 4. Minus pi by 4 is nothing but 3 pi by 4. So that way I can say directly my answer is B. Okay. For pure shear case, your principal plane will be like 45 degree and minus 45 degree. So you can say these are my principal plane, and the value of those principal stresses sigma 1 comma 2 is also plus minus tau. So sometime they have asked this also, what is the ratio of principal stresses? So it will be 1, right? For pure shear case, okay? And if you ask me for pure shear case, what is the tau max? Tau max will be also equal to tau. What is the plane of tau max? The plane of tau max will be what? It will be 0 and 90 degree. Okay, so these are the things we can learn for pure shear case. Now guys, how I got this pi by 4 and minus pi by 4. You guys know theta 3 usually we represent, sorry, not theta 3, theta 3 we represent for tau max. So theta 1. So what is the theta 1, guys? We know it is 1 by 2 tan inverse. Anyone? What it is? Tan inverse 2 tau xy upon sigma x minus sigma y. So these are the principle, the first principal plan, right? It's a first principal plan. So we know here sigma x is 0, sigma y is 0. So from here what we find? We find 1 by 2 tan inverse infinity, which is nothing but 90 by 2. So you can see it is 45 degree. So one is 45 degree. The another, we know theta 2 is always what? Theta 1 plus 90 degrees. So you can say 3 pi by 4. Okay. Anyone has any doubt in this? So let's do a poll. What is the answer? B is the answer. B is the answer. B is the answer. Okay. Now, guys, in exam they asked this pure shear case. But guys, you guys must start with like uniaxial cases, uniaxial loading. Then you guys can learn biaxial loading also. Okay. And then this is the third case is what? Pure shear case. Now, what is the uniaxial loading? Uniaxial loading means only you have only either sigma x, or you can have a case where you have only sigma y. Okay. What is the biaxial loading? Biaxial loading means you can have sigma x as well as you can have sigma y. But what is the tau xy in biaxial loading? We know biaxial means tau xy is 0. Okay. So for all these cases, what all the things you guys should know? What are my like stresses in inclined plane like sigma s, sigma t? Then what are my principal stresses sigma 1 and sigma 2? What are my principal plane theta 1 and theta 2? What is my tau max? What is my plan of tau max? Then also you guys must know like more circle, more 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 circle. Okay, more circle for all these cases, because first time in GATE Aerospace last year in 2022 they asked a question on more circle. So guys, can you do all these? I'm telling these for your quick revision or from your exam point of view, what is important. Clear, Saptadeep? Okay, so let's move to next question. What it says? Now it is a 2-mark question. Till now, the first 5 questions were for 1 mark. So what it says? A bar made of linear elastic isotropic material is fixed at one end and subjected to an axial force of 1 kilonewton. At the other end, the cross-sectional area of the bar is 100 mm square, length is 100 mm, and Young's modulus is 1 into 10 to the power 5 Newton per mm square. The strain energy stored in the bar is. So now if you see the bar, what they told, your bar is fixed at one end and free at other end, and there is a load which is of 1 kilonewton. Now you can see here your bar is what? Slender prismatic bar. Okay. So whenever there is a prismatic bar, what is your strain energy stored and how you can find? If you draw the diagram between the load and deflection, P and delta. So the area under this diagram is nothing but strain energy stored in this prismatic bar. So U will be what? 1 by 2 P into delta. And we know the delta for this prismatic bar is what? It is what? PL. What is the delta? It is PL upon AE. So what will be the strain energy? It will be P square L upon 2AE. Now guys, everything is given. We can find strain energy stored in Newton mm. So guys, do the calculation. So what is the strain energy? U. Now guys, if you see U, what is the P? P they have given as 1 kilo Newton, right? So it is nothing but 10 to the power 3 whole square. Then L, the length is how much? It is 100 mm upon 2. What is the area? 100. What is the E value? It is 10 to the power 5. So tell me what is the answer, guys? Yeah, 2AE. Yes, so guys, what is the answer? If you see, so if you find answer from here, it is 5 Newton mm. What is the strain energy stored in this? Is 5 Newton mm. Am I correct? Guys, can you check? Is this correct? Yes or no? So guys, the given question is from what? Axially loaded member. Axially loaded member, right? Which is what? Bar or rod. Is this 10 or 5? Everyone please check. I think 5 is correct. Yeah. So 5 is the correct answer. Suppose guys, in given question, your bar or rod is not prismatic. What it means? If anyone, like suppose your area or your materials or your area is function of x, or your material is function of x, or your load is function of x. So in that case, what will be your strain energy? It will be in integral form. So it will be 0 to L, which will be like nx square dx upon 2ax ex. So from these concepts also there are question in gate mechanical, and they may ask in gate aero as well. Okay, so this is for this wearing. Now suppose you have stabbed bar or rod like this. Okay, so in that case, how the strain energy? It will be like summation I equal to 1 to n. It will be nx square, or you can say not nx. It is ni square li upon 2ai ei. Okay, so all these cases you guys should remember from gate perspective. Okay, so let's move to next question. What it say? This question is again a question which is the combination of spring and beam. So read the question what it says, or basically it's a SOM question. So it's a 38 number question from Gate Aerospace 2016. A cantilever beam springs system is shown in the figure. The beam is made with a material of Young's modulus 1 into 10 to the power 5 Newton per mm square, and geometry such that its moment of inertia is 100 mm power 4, length L equal to 100 mm. It is supported by a spring of stiffness K equal to 30 Newton per mm and subjected to a load of P equal to 100 Newton at the point B. The deflection at the point B due to load P is. So guys, how to solve this question? So basically, this question also you need to idealize in, springs, okay? Two springs kind of system. Now guys, tell me this point B is what? A junction point, or you I can say I can ask you guys how this beam and spring are connected in series or parallel. These are in series, Satish. These are in series or parallel. If what is the definition of series, Vashant? Series means suppose this is my beam and if you connect your spring here and then you apply load, then it is what? Series. Why it is in series? Because this P load is not directly applied on this beam. But here what is the case? Here what is the case? You have a beam and the load is here, which is junction, and then there is a spring connected. So what this combination? Parallel or series? It's a parallel. It's a parallel combination. It's a parallel combination. Okay. Now guys, since it's a parallel combination, we can find what is the K beam, the equivalent stiffness of beam. So we all know, right? When there is a cantilever and the load is acting at the free end, the equivalent stiffness of beam is what? It is 3EI by LQ. Okay. How we find this? We know, right, guys? The deflection at free end, it is always what? TL cube upon 3EI. So we know stiffness, it is what? P by delta. So from here, we know the beam is stiffness. Now guys, this beam and spring is in parallel. So my K final will be what? K beam plus K spring. Now guys, what is the K beam? It is 3EI by L cube, and K spring is given, which is how much? 30. So guys, first find out K final. So what will be the K beam first? It is 3EI by L cube. So what is the E value in this problem? E is 10 to the power 5 Newton per mm square. What is the I value? It is 100 mm power 4. What is the length? It is 100 mm. So guys, find KB. So my KB, if you do calculation, it is coming as how much? It is coming as 30 Newton per mm. And we know K is also given how much? 30 Newton per mm. So what is the K final? It is KB plus K. So which is how much? 30 plus 30. So it is 60. And my final deflection, which will be how much? Delta will be what? It will be P by K final. So how much the load? The given load is how much? It is 100 Newton. So what is my deflection? 100 by 60. So how much is the answer? It is 1.67 mm. Okay, so this kind of question we have to solve like this. Clear? So this is another variety of gate question. Okay, so let's move to next question, 39 number question, and question number 8. What it says? It is again a thin walled structure question. Okay, and it is from thin walled structure. Again, you guys should know. I have covered this and I have kept one document also on functionality and the load supported by different structural element of aerostructure. So we all know, right? The wing structure. The wing structure will have several structural components like rib, spar, stringers, right? So if you draw the wing will have what are main structural component, guys? We all know what are main structural components for wing. What are main structural components for wing structure, guys? Anyone can tell? There are four main structural components. One is what? To maintain cross section is rib, right? Ribs. Okay. Then we know spars, right? Spars. Okay. Which will be running like this. Okay. Along length of the beam, and ribs will be along, you know, your cord of the wing. Okay, and then stringers, there will be small structures, stringers. Okay, stringers, and then this is skin. Now guys, what they asked in this problem, they told, the statement A says ribs used in airplane wings increase the column buckling strength of longitudinal stiffeners. Okay, so guys, see, you know, this, what is this longitudinal stiffener? What is the longitudinal stiffeners? We all know the longitudinal stiffeners is spar. So what happened? This spar will be connected with, you know, multiple ribs, right? Right. So what it is going to do? This longitudinal stiffeners, okay, is spar, and then there are stringers. Okay, small stringers will be connected. So what basically ribs do? Ribs will divide your skin in multiple panners, or in this longitudinal stiffeners in multiple numbers. So that means if the length is decreased, it will increase what? Buckling strength. Okay, so basically this rib will increase buckling strength. But how it will increase? It will increase by redistributing concentrated loads into the structure and redistribute stresses around discontinuities. Okay, so wherever they are connected ribs, they will, you know, redistribute stresses at those discontinuities. Okay, so both A and B, A and R are true, and R is the reason for A to increase the buckling strength. Is it clear? For this, I have shared one document by IIT Kanpur professor. It is kept in our drive, so you guys can refer, you know, those IGC students to learn more about this aircraft structural elements, their functionality, and the load, you know, supported by them. Satish, is it clear? Question? So both A and R are true, and R is the correct reason for A is the answer. So July batch, guys, these topics you guys have not learned with me should be done by self-study. Vashant and even Satish, because due to lack of time, we haven't moved in this particular point during classes. Crash course, people. Okay, let's move to next question. Yeah. So another thin walled structure question, and easy question. What it says? So this question is from torsion of thin walled structure. So another easy topic in thin walled structure is what? Torsion. Okay. So I will suggest those who are afraid of thin walled structure, they must study at least torsion of thin walled structure. So you can solve this kind of question easily. Yeah. Yeah. In May and Feb batch, I have done that. Okay. So read this question, what it says. A channel section shown in the figure has uniform thickness. It is subjected to an anti-clockwise torque of 62.5 into 10 to the power 3 Newton mm. The maximum possible thickness of the channel section such that the shear stress induced in it doesn't exceed 100 mm square. So guys, it's what? Open section or closed section, guys? If you see this section, open section or closed? It's an open section or closed section? It's an open section. And we know what is the torsional formula for thin walled open section? For thin walled open section, my torsional formula is given by what? T by J equal to what? Z theta by L equal to tau by T. Okay, tau by T. Now this for thin walled open section, what is this J? It's a torsional constant, right? This is torsional constant. And how you find, guys, this torsional constant? In this T by J equal to G theta by L equal to tau by T. What is this J? Is torsional constant. Okay. Now guys, this J for thin walled open section is given by what? 1 by 3 sigma BTQ. Yes or wrong? This is the formula you guys can remember. If your thicknesses are uniform, like this is one section, this is section 2, this is section 3. If your thicknesses are varying, so in that case it will be in integral form. So which will be y? Which will be what? In integral form. Okay, if your thicknesses are varying. So in integral form also you guys can remember this formula. But in this case, your thicknesses for each section, it's uniform. Okay, so guys, it is what? In that case, it is T cube dx upon 3, like that. Okay. Now guys, what is the J value in this case? It is 1 by 3. Now you can say each section has, what is the length? B value is 100, 100 and 100. So the total sigma length is how much? 300. And what is the thickness for each? for each section my thickness is unknown. Okay, so thickness is unknown because they asked what the maximum possible thickness. Okay, so TQ. Okay, now or you guys can write it like this 1 by 3, then like 100 into T cube plus 100 into T cube plus 100 into T cube. Okay, so like that we can write. So which is nothing but J this. Now guys, what is this given? Tau. The allowable, they given allowable shear stress, which is like doesn't exceed 100. So tau allowable is given 100 Newton per mm square. Now guys, we know from torsional formula what T by J equal to tau by T. Okay, so what is this tau? It is T by J into T, and tau is given as 100, and T is how much? 62.5 into 10 to the power 3 upon 1 by 3, 300 into T cube into T. So what is the T square? What is the T square, guys? So what will be T square? So T square will be, I think, 6.5, right? $6.25. Yes. Then what is the T? It is 2.5 mm. 2.5 mm. So clear, guys? Was it tough question? It is an easy question, guys. So guys, all of you must know torsion of thin walled structure. So in this torsion of thin walled structure, first it is a Brad-Beddoe theory. What is Brad-Beddoe theory, right? So what is the Brad-Beddoe theory? T equal to 2AQ. Then this is for single cell. If it is a multi-cell, then it is 2A1Q1 plus 2A2Q2 and so on. Now the second formula, which is like angle of twist. So you guys should remember for single cell, and for multi-cell it is what theta1 equal to theta2 and so on. Then this is for what? Closed section. Closed section. And whatever we discussed, this torsional formula is for what? Open section. So not many formula in this torsion of thin wall. You guys can prepare this topic well for your gate preparation. So let's move to next question, what it says. So this next question is from mechanical vibration. Okay. And this is from which topic? It is from damped free vibration. It is from damped free vibration. What is given? The governing differential equation for damped system, it is d square x by dt square plus c dxt plus kx equal to 0. So that is nothing but like mx double dot plus cx dot plus kx equal to 0. Now here mass is given 1 kg, c is coefficient of viscous damping is 2 Newton second per meter, k equal to 2 Newton per meter. What is asked? Then the natural frequency of the damped oscillation of this system is. So we know what is the damped oscillation frequency? Omega d, which is nothing by under root 1 minus zeta square omega n. Now here what is the omega n? Guys, it is under root k by m. And what is the zeta? It is c upon 2 under root k m. So guys, first find out natural frequency and find zeta, and then find damped frequency of the damped oscillation. So guys, my natural frequency is coming as 1.41 radian per second, and my zeta value will be coming as 0.707. Now when we substitute this in this equation, what we get? We get 1 radian per second. So guys, please check, are these correct value? Are these correct? So those who are watching on YouTube can answer, are these correct? So guys, again, this damped free vibration is another very important topic in GATE Aerospace, and another concepts which is what from damped free vibration is what? Logarithmic decay. So logarithmic decay is given by what? 1 delta equal to 1 by n ln of x naught by xn. So what is the n value? Which is like many people will have confusion. It is always calculated by nth cycle minus first cycle. Okay, now first cycle is what? 0th, and in this case nth cycle is n. So the value of n is what? N minus 0. But in some cases they give like you have second amplitude and you have 9th amplitude. So what will be the value of n, Mr. Vashan? What will be the value of n? Will it be 8? Will it be 9? With what it will be? So it is like 9 minus 2, so value will be 7. Okay, so this you guys have to take care. Another mistake people do, when it's asked the ratio of amplitude, it is e power 2 pi zeta. It is not 2 pi zeta, because we know delta is almost equal to 2 pi zeta, and which is again nothing but 1 by n ln of x naught by xn. Okay, so guys, be careful in that. So this is the last question, and it is from Airy stress function. Now guys, again I am telling, from Airy stress function they haven't asked questions, I think, from last 2-3 years. Okay, so they may ask a question from this Airy stress function this year, and they have asked several questions in earlier GATE paper from Airy stress function, and it's a very easy topic from basic elasticity and another important topic. And I have provided one YouTube lecture on this topic, Airy stress function and compatibility equation. So those who are watching on YouTube channel can refer that lecture. Okay, and almost 8-9 questions are there from this. So what it says, read this question guys. The two-dimensional, it's a 11th number question guys. There are total 11 questions in this GATE 2016. What it says, the two-dimensional state of stress in a body is described by Airy stress function phi equal to, so it is given function of what? X and y. What it is given? 5x power 4 by 12 plus x cube y by 6 plus 3x square y by 2 plus 7xy cube by 6 plus e, which is unknown here, y power 4 by 12. Now guys, what it says, the Airy stress function will satisfy the equilibrium and the compatibility requirements if and only if the value of the coefficient E is. So we know Airy stress function satisfy your equilibrium equation and compatibility equation when if it satisfy biharmonic equation, right, which is what? Delta power 4 phi equal to 0. So if this is the case, means by default it satisfy equilibrium and compatibility equation. Now what is this equation, guys? It is like dou power 4 5 by dou x power 4 plus 2 dou square 5 by dou x square dou square 5 by dou. No. It is not like this. It is 2 times dou power 4 5 dou x square dou y square, I think. Yes, guys, please check. Yes, correct. Then plus dou power 4 5 by dou y power 4. So this is what my Airy stress function equation. Now guys, this phi, if you substitute in this equation, you need to differentiate. Okay, so when you differentiate this phi, like with respect to x 4 times, when you differentiate this d, or if I write here d power 4 5 by dx power 4, what you get? You will get, when you differentiate this equation, you get what? 10. You guys can check. In second equation, if you write 2 times dou power 4 5 by dou x square dou y square, what we get? We get 2 into 6. And last, when you differentiate with respect to y 4 times, what we get? We get 2e. Now we know this equation what it is. It is 10 plus 12 plus 2e equal to 0. So from here, what is the value of e? What is the value of e, Mr. Varshan? What is the value of e? E will be coming as minus 11. Now if you look this question, it is of what? It is of more of what? More of what? Anyone tell? It is more of math, right? The only thing which you need to remember is what? This Airy stress function equation. Like Airy stress satisfy biharmonic equation, which is what? Dou square phi, dou power 4 phi equal to 0, which is nothing but dou 4 phi by dou x4 plus 2 dou 4 phi by dou x square dou y square plus dou 4 phi dou y power 4 is equal to 0. So is it clear? So this question clear, guys? Any doubt? So guys, these are our contact details. You guys can contact us for any further support for GATE Aerospace Engineering. And our upcoming batch is from Feb 19th, okay, for GATE 2024. So thank you guys. Thank you very much. You guys can follow us on Facebook, Twitter, Instagram, LinkedIn, YouTube, Telegram, and IGC is one of the most professional institute for GATE Aerospace Engineering in India, and we are the best, one of the best place, or in fact say number one GATE Aerospace coaching institute. So thank you all for joining this session, and let me know if any doubt. Mr. Varshan, clear, right? Okay. So thank you all. Bye guys. Good night. We'll meet tomorrow with another session. We'll meet tomorrow with the GATE 2015 paper.